Hello, everybody. Today, Mohammad and I are going to talk about semi-supervised data cleaning with our two systems, Raha and Baran. Just before we start giving you the demo of our systems, let me try to motivate again the reason why we built these two systems. Imagine a made-up situation, a strategic meeting within an organization. They look at numbers, they see that the numbers are not looking good, they might want to improve them. So what they do is they say, okay, we can reduce costs by just improving data quality. That's pretty common. So we need to clean our data. Let's ask a cleaning expert who will come and help us. He will say, no problem, let me show you. This is a piece of code with state-of-the-art data cleaning. You just give me a data set and I clean it for you. Oh, that's amazing. How does it work? That's how people usually react. Well, we need some data constraints to find the errors and fix them for you. And that's a true story. They will not know what constraints are. They will ask, do you have the data constraints for us? And of course, you will say, no, we don't have them. The organization, the user has to provide them. What are those constraints? They will ask. For example, this could be denial constraints or functional dependencies. That's how you encode them into state-of-the-art systems. And that's a bit unlucky for the organization because they find it most of the time too complicated and they don't want to do that. And then you say also, oh, by the way, you also need to adapt the cleaning tool to your data set because there are a bunch of parameters that need to be tuned. That's also not something that they might want to like. And they come and try their best to find a better solution. Can you do that without all of that, without the rules and parameters? And the data cleaning expert might ponder and just will ask, can you give us at least some annotated tuples? And then you say, that's possible. We have some domain experts that can tell you which which tuples contain errors and how they should be fixed. And then the data cleaning experts will say, here, there are two systems, Raha and Baran. You just give us your dirty data set, a few user annotated tuples, and it will clean it for you. You just need to pip install Raha and it will work like a charm. And Mohammad will tell you how it will actually work while presenting the demo.
Hello everyone, I'm Mohammad and I'm very happy to present you two Jupyter notebooks today. And in these two notebooks, I will showcase our Raha and Baran systems in end-to-end data cleaning pipelines. In the first notebook, I will show you a minimal pipeline to showcase how we can use these systems in action. In the second notebook, I will show you a detailed pipeline to drill down three aspects of these systems. So let's start with the first minimal notebook. As you can see here, we just need to first import necessary modules. In particular, we need to import Raha's module, which is installed by using command pip install Raha. In the next step, we need to instantiate detection and correction classes of Raha. As you can see here, we do not need to provide any rules or parameters. We just need to set the labeling budget of these systems, and we also set a flag here to just print internal logs of these systems. In the next step, we instantiate our dataset class. So here we have a simple dataset. We have its name, its path, and also its clean path. We use the clean version of the dataset to just evaluate our data cleaning task at the end. In the next step, we need to generate features for each data values of our dataset. So the features are basically generated based on the output of a set of error detector strategies that mark data values of dataset as data errors. After generating features for each data value inside our dataset, we can also build hierarchical clustering models, which model the similarity of data values based on their similarity of their feature vectors. In the next step, we need to ask the user to label a few data values for us. In particular, the user takes a tuple at a time, and the user needs to mark and fix the wrong data values. Whenever the user wants to label a value, the user can simply change it to another value, as you can see here. Once the user changes one value inside the sample tuple, we store two things. First of all, we store the original value of that attribute value as a data error, and further, we also store the new value that is provided by user as the correction of that particular data error. So due to the time limitation, I use the ground truth of dataset in this presentation to label 20 tuples for the rest of our data cleaning task. In the next step, the system, Raha, propagates user labels into the cluster of that particular data set. So by doing that, we can increase the number of labeled data values, as you can see here, from 140 data values to more than 12 labeled data values. And at the end, we train a classifier per data column to predict the label of the rest of data columns inside our dataset. So next, we need to update and fine-tune our error corrector models based on the user-provided data values. By doing that, our error corrector models learn to propose the actual correction of our data errors. So at the end, we can visualize the progress of our error detection and error correction steps. As you can see here, we can see the number of detected data errors per attribute inside our dataset. And in the second chart, you can see the number of corrected data values per label tuples. And after that, we can simply store our data cleaning pipeline in terms of error detection and error correction tasks by simple APIs that we have here. And finally, we can evaluate our data cleaning task in terms of error detection and error correction by using the ground truth of the dataset. As you can see, we can achieve high precision, recall, and F1 score with this simple pipeline that uses only 20 label tuples. So that was about a minimal pipeline to showcase the functionality of our system. Now let's look at the detailed pipeline. In this detailed pipeline, I would like to focus on 3 aspects of our systems. The first one is about transfer learning, how we can use already cleaned data set to optimize the current data cleaning task. The second aspect that I want to show you is about how the label propagation and classification increase the number of user label tuples. And finally, I would like to show you how we can inspect each corrected value to see which error corrector models propose that pattern. So let's assume we have a couple of data sets that are already cleaned in the past. We call them historical data. So here we have 2 historical data, hospital and beer. For these 2 data sets, we have both the dirty version and the clean version of the data set because we already cleaned them in the past. So we can use this already cleaned data set to optimize the current error detection step. So here, we calculate one score for each error detector strategies that we have. So that's why we can sort these error detection strategies based on their performance on similarly dirty data sets in historical data. For example, our outlier detection strategy that works based on the histogram algorithm with parameter 0.7 has the highest score, 92%, because the tuple ID of the current data set slice is similar to phone column of a historical data set, which is hospital here. Why is it good to sort the error detection strategies based on these estimated scores? Because then we can filter out ineffective error detection strategies that have low scores. And that decreases the number of error detection strategies that we need to run on our data set from 500 to around 200. And why is it good? Because we can reduce the runtime of running all the error detection strategies from 200 seconds to around 100 seconds. And this can be done using historical data that we had in the beginning. So that was about the first aspect of our system. Now let's look at the second. We want to see how label propagation and classification increase the number of label values that we have. Here you can see a 2D visualization of our data values inside column actual arrival time. So how do we do that? We project the multidimensional feature vectors of our values into a 2D feature space. So that's why we can simply visualize them. So here we have only 20 label tuples, and that's why we have 20 labeled value inside this column. The red values here are labeled as dirty by the user, and the clean values inside this visualization chart are those values that user labeled as clean. And the rest of data values inside this column are gray, which are unlabeled. So we do not know whether they are clean or dirty. So after clustering data values based on their feature representation, we can propagate user labels into the clusters of those particular data sets. And that's good because we can increase the number of labeled data values. As you can see here, now we have more green and more red data values because we propagated user labels into the cluster. But we still have a set of unlabeled data values. And that's why we need to train a classifier per data column to predict the rest of data values. As you can see, the rest will predict the label of the rest of data values. And now we have all data values either green or red, which are clean or dirty. So that was about the second aspect of our last aspect of our system that I want to show you today is about how we can inspect the detected and corrected values inside our system. Here we have the list of data cells that we are already detected and corrected using Raha and Baran. For example, we have here a cell which is inside this tuple, and this cell is here basically actual arrival time, and it has the erroneous value 4:05 p.m. And the actual correction of this value, which is predicted based on the feature vectors that we had, is actually 4:17 p.m. So we can inspect which error corrector models that we had proposed this actual correction. In particular, we can see here one error corrector model which works based on the function dependency between flight column and actual arrival time proposed this actual correction for this data error with 100% probability. And that's why the classifier of this column can understand that this particular error corrector model is one important feature to predict the actual correction of data errors inside our actual arrival time column. We can also mark this value in blue inside our 2D projected data values of this column. And that was about the last aspect of our system. Let me conclude our presentation. Raha and Baran are semi-supervised data cleaning systems. These systems are configuration free and they do not need any user-provided rules or parameters. We can simply build end-to-end data cleaning pipelines using Raha and Baran, as you can see inside these two Jupyter notebooks. If you are interested to use Raha and Baran, you can easily install them by using pip install Raha command. And you can also find our codes and Jupyter notebooks, documentation, dataset, everything inside our GitHub repository, bigdama/Raha. Thank you for your attention. I would be